Hello everyone, this is Mohsen Saraj. I'm an application engineer at Ozen Engineering technical team. In the previous part of this video, I already talked about how to model a pipeline for crude oil that is schematically shown in the bottom of this slide, that the oil from tankers delivered to a marine terminal floating on the sea level and then sent out through the pipeline at the depth of 35 meter below sea level toward the booster station on land, and from booster station transported to the salt facility. For you as the maintenance engineer for this pipeline, it is very important to know that what is the effect of ambient temperature on the crude oil properties that could affect the mass flow rate along the pipeline. So I already talked about how to create a new fluid material to model crude oil properties in terms of the properties given in this table at the bottom of the slide, and also what are the effects of adding heat transfer elements to the system to model the heat conduction and also thermal inertia of the pipe walls, and what are the effects of these heat transfer elements on the pipeline delivery. Now in this video I want to work on the last part, that what's happen if the offloading crude oil temperature changes from 20 to 60 degree, and how can I model this variation within Flownex environment. Watch this video. This is the pipeline network that I adapted from one of the Flownex tutorial for crude oil example. This part from the single point mooring, and this is for the floating terminal. Next part it is for booster pump stations, and the last part it is for salt facilities, salt dome storage facilities. And I'm considering three heat transfer elements here. I already solved this in pipeline when the deployed oil is 60 degree Celsius temperature, so it is like a warm oil. This is the temperature distribution along the pipeline, and we can see that specifically at the parts that we have overland pipeline, it is a kind of cooling that we have for the oil, and we have heat dissipation to the environment, to the surrounding air. For example, here you can see that at this pipe the temperature is about 30-31 degree, or the temperature at the storage it is about 30 degree. So let's change it to this problem to the cold oil. So for this heat boundary conditions, at the very beginning I changed the temperature from 60 to 20 and go to home tab button and solve this for this new boundary condition for 20 degrees Celsius. We call it like a cold oil. It is solved. Let's check the temperature distribution. This is interesting that you can see that we have lower temperature at the parts for the pipeline that is overlapped. Like here you can see that about 17 degree, 17 degree, 18 degree, and after adding the heat transfer to the pipe it goes back to about 19.4 and about 20 degree. So now instead of cooling down the hot oil, we have cold oil, and at the part of the pipeline it is heating up from the surrounding air. So far we have the results for two cases. One case when the temperature of the crude oil it is 20 degree, that I can call it cold oil. And previously I solved this network when we have the temperature of 60 degree for the crude oil, that is like a warm oil or whatever. So in the last part of this problem, I want to see that how when we change this temperature from 20 degree to 60 degree, what's happened to the temperature in the other parts of the network, and also what are the change in the flow density. And you remember that previously we had about 30,000 kilogram per second for the mass flow rate. Now for the temperature of 20 degrees Celsius, it is the mass flow rate, it is like as you can see 2850 kilogram per second, that you can see here in the for the last pipe. And if we check it here, you can see that 2850 for the that. So from 30,000 decrease to 2850 is about 5% decrease in the mass flow rate. So we see that the viscosity of the oil really affects by the temperature. Let's work on changing the temperature from 20 degree to 60 degree. For transient or dynamic simulation in Flownex, first of all, we need to set a scheduler to specify the inputs for transient simulation. Then we need to create a scenario and define the necessary action that shows that what are the properties changed during the simulation. We can have a setup to see the time-based time-based results during the solution and how it's changed during the time. And also we can have we can create a snap or a snapshot to save the simulation results at a specified time, and then we can reload it anytime if it's necessary. So now we want to consider if the oil temperature suddenly increased from 20 to 60 degree. What's happened to the temperature distribution and the the resulted viscosity or mass flow rate? Okay, let's set up the scheduler. Come here to solver, and you can see that here it is the scheduler. Some we need some setup here for running mode. For the running speed, running mode, we can say that's fast as possible. And also for time steps, we can say that first of all we start with adaptive time step instead of constant time steps. We can specify the uh, simulation duration to specify by n time, and it is already like a 24,000, like about 6 or 7 hours, to see that what is the effect, long-term effect of the changing oil temperature. So this is what we have for the scheduler. Let's come here to set up the scenarios and action. You can come here to the configuration and action setup. Click here. As you can see that in the left pane we have scenarios. Click new scenarios. We can rename it for whatever we want. Say that, for example, warm oil offloaded. Okay. oil offloaded. And in this part we can have the new actions. If we want, we can add it here. Okay, what we can do is that we can click here on the first uh, boundary condition here at the beginning of the start point of the network, have this temperature, click on that and drag it here. So you can see that now we have an action that it is the input for that, it is the temperature of oil at the start point of the network. Be sure that the trigger it is at 0, and we want to see what's happened if the value suddenly increased to 60 degree. So we're done for defining the scenario and a new action. To define the graph, come here and click on the graph. So inside project view, graph, right click on graph, add a new folder. We can call it, for example, temperature, and add a new graph page. You see that we have various and different types of the graphs. We can add line graph here and call this also temperature. So you can see that a new page opened and now it is blanked. So for temperature, click here to see the properties, and you can see that here we need some information here. Let's first define what we want to have here for the line graph. We can add items here, line item 1. Okay, for the properties here, you see that what we want to add it. We choose here the node n, which is the node at which is the very first node at the pipeline. Check here for the result, be sure that we have it in the result, and check total temperature. So we want to see that for the node right after the boundary condition, the start point of the network, what's happened when we suddenly change the temperature from 20 to 60. We have this here. For the name, we can call it SPM inlet node. So we're done for this one. Add another one. Go here to the properties, and now check the inlet node for the terminal, which will be node N2. This one is, they say that marine terminal inlet. Again, result, we want to see what is the temperature and name this as terminal inlet node, and we can add another one which will again we go to the properties, and this one now will be the reservoir, and we want to see what is the temperature of the reservoir. Again, inputs for the results and same static temperature here. Name this reservoir. Okay, So we're good. As you can see now, we have three line graphs that we defined it here. So now let's set up the graph. We can have the set the graph formatting. Then come to y-axis here, and as you see that it is time based, which is correct. And for the y-axis, instead of one for each item, we just say that just one for all items together. You can see the legends for the graphs, for the line graphs here. As you can see, it is already defined. Auto scale, yes, for that one. And for the title, we can say that it is temperature, type it Celsius, okay, and unit group also will be Celsius for the temperature. Here go. Running mode, we can have it to time based for the recording in the history recording. That's okay. And maximum display length, we can say that it is 25,000 seconds. So we can now save it. Now if we want to add a snap here, you can come here to window and snap. Okay, I already created this snap, but you can have it say that new snap. I changed it to 60 degree, and say that after that we can say the right killing and load it, so it will start saving the results. So back to home page. First we solve the steady state. Okay, this is the results for a steady state. As you can see, the temperature changing here. This is what we had before. And for that, now we can run the transient simulation, but hit the run button here. It will start, and you can see also the graphs that the first one is the first node in the network 60, same as the boundary condition that we apply, suddenly start from 20 to 60. But we haven't seen so far the effect of sudden increase in the temperature for the inlet point for the terminal and for the reservoir. And if you cannot see this live results, you can right click and set as show point value. And here also we can see live changes to the temperature. Okay, you can see here, but it is at the very beginning. Now it is just 420, we have 25,000 seconds. So let's see what's happened. We now pass 600 seconds. So we hope that we see the effect of this sudden increase in the oil temperature at the inlet for the terminal soon. That you can see it here. This is red line is for the terminal, inlet of the terminal. Now you can see that it starts rising the temperature at the inlet node at the terminal, the temperature. And you can see here this one. It is now, you can see that the temperature is increasing to 25 and then go up to 26 27, 28 degrees Celsius. Back to the graphs. This temperature is rising. Now 1200 seconds passed, and you can even come here 6% of the total time. So at about almost 850, 860, okay, sorry about here, 840, at about 840 seconds, we see that the temperature of the terminal inlet passes 21 degree. We can check instead of temperature change in the mass flow rate. It was 2850 for 20 degree. Now we see that increasing to 2864 here. It start increasing. Time is now about 2000 seconds about, and the temperature at the terminal inlet now is about 55, something like this, 55 degree. So it is the change in the terminal temperature inlet is, it just start flattening. The graph start flattening. The mass flow rate increased to 2870, 71 here, up to here. So you can see that the graph, the line graph for the temperature of the terminal inlet, it is flattened and unchanged. It is at about 55 degree. If we check the temperatures distribution along the pipe, you can see that the larger temperature, higher temperature start to that we can see it in a larger portion of the pipeline. Here you can see it is temperature, it is 55.6. This is what we are seeing here, 55.6. So now it is 3500 seconds passed. So we have long time until 25,000 seconds. So I'll show you the results time by time, but it will take about maybe 10 minutes to finish the solution. Now more than 6,000 seconds and more than 25% of the solution done. You can see that the temperature is fixed for the inlet terminal to 55, and for the reservoir it just constant at 20 degree, 20.4, and you can see that here the change in the temperature along the path line, and also mass flow rate. Now it passes 2900 kilogram per second. So now is about 7,000. Yeah. We are now at 12,000 seconds, about 50% of the solution done. Again, that's constant temperature for the three graphs that we are seeing, that the mass flow rate increasing toward 30,000 kilogram per second that we had previously for 60 degree, So now it is about 2950 almost, that you can see it here. A little bit more or less, they are very close by. And the temperature now is the maximum, it is 60 that you can see here. It is 55 constant at the inlet of the terminal, 56 degrees Celsius, 57, and here as you can see 30. It reduced. This is the effect of seawater. 18,000 second, 19,000 second pass, more than about 80% of the solution done. And now for the mass flow rate, you can see that we're approaching 30,000 kilogram per second. Now it is 2974, 5, something like this. And this is the mass flow distribution. And for the temperature also, you can see that the temperature for this one, it is almost 20.4 for the reservoir. So these are the ones that we are seeing here, that it is 20 something, 20.4 for the reservoir, 55.6 for the terminal inlet, and also here 60 degree for the first node. So 24,000 pass, we almost done. Yeah, solution is finished 100%. This is what we have from the graphs. If we back to the network, you can see that similar result we can have it here. If we check the result here, 55.7 or 8 almost degrees Celsius, and for reservoir the temperature it is 20.4. So you can see the effect of rising, sudden rise of the temperature at the beginning when the oil deployed from 20 to 60 degree. This effect is we can feel it inside the pipe up to the terminal and after that, but as we going towards the reservoir, it is damped, and it is because of the thermal inertia that we have inside the pipe. So that's why we cannot see really the effect of this increasing from 20 to 60 degree at the start point of the network on the reservoir as the end point of the network. The mass flow rate almost 30,000, 2990 almost for this one. If you check, we come to the results, and for the mass flow rate, okay, no, yeah, mass flow rate, it is almost 2990. So it is just 10 kilogram per second less than 30,000 that we already saw before when we solved the steady state solution for the temperature of 60 degree at the beginning. So to sum up, what we have done is that we started first with a scheduler, and we set up the transient simulation here. For example, what are the endpoints? Okay, what are the, as you can see, the time steps. It is just because it is adapted. I started from 200 millisecond, ended up to 30 349 milliseconds. The scheme for the solution, time steps, running mode, these are the things that we can work on that to set up the transient simulation in Flownex. After that, we need to come here to configuration, and for the action setup, I already as you can see, I added this scenario and this action, that the action is for temperature of this uh, temperature of this boundary condition at the beginning of uh, the network, and I set the value that suddenly goes from, now it is 60 but it used to be 20, goes up to 60. So this is the action that I have. Next is graph. I define a graph here. As you can see, this is the graph that I have, and for the properties of the graph, you remember that I add three line graph here and define it based on the output parameters that I'm interested, that it was the temperature can be assigned to an element. Here for example I set three line graphs, one for the first node right after the boundary condition or start point of the network. Another one, it is the for the node that before the terminal, we call it terminal inlet of the terminal. And the last one, it is for the reservoir. And the last part is to go for a a snapshot, and load it to save the result. And at the end I first run steady state and then run the transient simulation by hitting the run. So I hope you enjoyed this video. Thank you so much.